All right, I handed back the method of sections problems. Those ought to be graded. So just a quick run through those so that we know how to do those. So here we go. Here's the first one. This one most people seem to do pretty well at. We get the reactions. We're going to make a cut through the truss. We want to find the members in the middle. So just cut through the middle and then go through and find equations that you can use. The theory behind this is that after you find the reactions on the truss, what you do then after you make your cuts is anything you don't cut through, just think of as being like a solid object. And then the things that you do cut through are then forces acting on it. So there's one, and there's one. So it's just an equilibrium problem, and you just then need to solve it out. So if you want to find that force CF, you just go sum of Fy. You got 22.5 up, 20 down, and sine of the angle times FCF down, so you can solve for FCF. Okay, doing all right with that? I think so. All right. You might then, working the same thing, take a moment about C there. That will allow you to solve for FFD. 25.5 times 2 meters clockwise, so that's minus, and then what? Sine of, what are we after here? I'm sorry, we're going to get, we're taking a moment about C, so we're going to take 3 times FFD, because this is 3 meters. That's how you'd solve for FFD. Are we all right with that step? Okay. And the last one there, you've got 2 of the 3. Okay. So the last one then requires you just to go sum of fx, and you could solve for FFD. You would have, and I got an error on this, a typo, I'm afraid, so let's get that fixed. It would be cosine 36.87 would precede the 15. That goes in there. That will go away. And then plus 4.17. And that would then get you FCE. Is that, not sure about that. Let's see. We got tension there. What do we got on this thing? Should be compression, FCE. So are we okay with that? FFD, oh, there we go. I got some problems here. This should have been 15, right? And then this is CE up there, I think. There we go. And then I have some labeling problems on that. And then FCF is 4.17. There we go. Now we're getting through this. This is 4.17, and this is FFD right there. There we go. Okay. So are we okay with the approach on the first one? You find the reactions and angles first. Then you make a cut through the members you want to find, and then you just figure out ways to solve them using regular 2D statics. Sum of Fy gets FCF because it's the only unknown acting in the y direction. The next one to get would be FFD, which would be, take a moment about C to accomplish that, because FFD, which is the other unknown, goes through C. So I don't think that's FFD, is it? That's probably, oh goodness, that's CF. I'm sorry about this. That's CE. Okay, so that's FCE. No, that's CF. That's good. All right, but this is not FFD. This is FCE. Is that correct? Yeah, okay. There we go. And that, so then you take a moment about C, and you solve for FFD. And then you take, once you've got that, you can go sum of fx and solve for fce on the top, and that comes out to be 18.33 compression. There we go, and that equation as written is correct there. All right. I just had some labeling that was incorrect on that. So we all right with that? Okay. Okay. Now this next one here, a little trickier. So these are some of the more involved ones. Here you need to find the force in EG. So I started by finding the reactions and the angles. DG is 33.69 and EG is 53.13. And then the reactions are 1600 up there, 2800 to the left there, and 2800 to the right down here. Okay, so that's where you start. Now you want to find the force in EG, this one. Okay, so usually you start these by finding the reactions and angles. Okay, I think most people got that right. Now, the next thing I would look at would be, okay, if I want to find that force, what happens when I take a cut through it? So here's the normal place to take a cut through EG, and you see you're going to run into some problems there because you have 4 unknowns. That is 1 too many. Okay, so if that's 1 too many, you need to find an independent way to determine one of the other unknowns. You need either another cut, or perhaps you could find the force in some panel nearby and then work your way into that location that I've cut through. I think the approach I would take on this would be to generate a second cut that goes something like this. If you make a cut like that, you'll be able to solve for DG, and you could probably do it by taking a moment about F, because of the four forces you've cut through, 3 of them intersect at F. So a jagged cut like that is perfectly legal. The only thing you can't do is cut through a joint. So if I make that cut, I should be able to solve for DG independent of the first cut that I made. So that would be one way to solve that. Okay, so I start by making the red cut there on the right, and when I did that, I saw that I can't solve it out by just using that cut. I've got to do something else. So the something else in this case, one option for it is to make the cut shown. Okay. So when I make the cut shown, I get a free body diagram, something like that. That looks on the left. And notice that 3 of those unknowns all converge on F. They all point to F. So I can take moments about F, and I do not have to worry about those 3 forces, CF, BF, or DEF there. Okay. So when I do that, then I'm going to use the left-hand side. I'm going to go 8,000 times 1.2. That's this one. That'll go counterclockwise, so that'll be positive 8,000 times 0.6, or the next one, that's this one, positive also, and then the one I'm after is FGD. That's going up at a 33.69 degree angle, so I'm going to use the cosine of the angle times FGD, and then that distance from F up to where that force is applied is 0.8 meters. So I can work through and find GD. It's 21,633 tension. Okay. All right, so I'm going to get that. And then once I've got it, I can then go back to my original cut that went straight through. One of those is now unknown. DG is now unknown, so now I'm down to 3 unknowns. I can take moments about I there and solve out the one I want, which is EG. Okay. So that's the approach on that one. A little bit more advanced because you had to make 2 cuts to figure it out. Make the first cut, you can see it's not going to be enough, so you look for a second thing you can do. Yeah, question there.
Is 2 the max, or is it just
I'm sorry, no?
2 cuts, like the
Oh, no, you can make as many as you wanted. You know, you could analyze it in any way you wish. The only rule is you can't cut through a joint. Other than that, you can pretty much do anything you want. And you know, I've never seen them where you need more than 2 or maybe 3, but you know, once you get beyond that, it's getting a little bit, I don't know.
Pick a better spot.
Yeah, right. What's the point or something? Yeah. Yes.
So when we took the moments about F, we were solving for which number?
When we took the moments about F, that was to get DG.
That was to get DG.
Right,
and then
this
use
one.
that to-
Yeah.
As one of your unknowns for your first cut.
Right, because see, the problem was the first cut had 4 unknowns. I got to get one of them out of there. And so the whole purpose of doing that other step was to get DG. That was the one I could get. Now it's known. Now that original cut will work. That's the thinking on that. Okay. All right, so, okay, we're good with that. And I'll post these in Moodle, you know, these keys, if you like. I'll clean up that first one, which has some typos on it. Okay, the next one there, we're after BG. It's kind of a similar thing. I make that cut. I got 3 unknowns, but it's still a little bit messy. I can handle it with that cut, but there's different ways I can go from there. I get the reaction. It's 8.09 on the left. Okay. Now, when I do that, one way to figure it out is I'm after BG. That's the one I want. It's this one. So if I can figure out where the other 2 intersect, which I'm calling point I out here, I could take moments about I and solve for BG after I find the reactions, of course. So I went ahead there and found where I is at, where it's located. And the way I do that is I look at the slope of BC. I'm going to push that down to the bottom there and intersect it with the horizontal. The slope of that is 1.6 to 2. Okay, that's the slope of BC. And then what I'm going to say here is if I want to come down here from this location right there, I got to go 2.4 down, and I want to know how far I got to go to get there. Okay, so I'm going to just cross, and these are equal. They're equal ratios. So what I'll do, I'll just cross multiply and get 4.8 is equal to 1.6x and solve for x. It's 3. So it's 3 meters out to I. Okay. Just doing a slope ratio there. Okay. And then once I've got that, so I'll just take a moment about I. And I'll solve directly for BG, 4.14 compression. So that's one way to do it. A little bit more advanced strategy, but a quicker way to solve it out. Now the other way to do it would be to use that original cut and just solve for BC first. Maybe take a moment about G and solve for BC. Then after you've got it, you can then do some of FY and solve for BG. That'd be the other way to do it. Okay. All right. So the other way to do it would be to start with the sum of moments about G with your original cut. Given that, you can solve for BC, and that comes out to be 5.24 compression. After you've got that, then what you can do is go sum of Fy and set that equal to 0. And then you can solve for BG. So you can do it either way. Okay. So I just thought I'd just go over that. There seem to be, these are probably the most advanced, some of the most advanced equilibrium problems we do. So I just thought I'd go over those a little bit. Okay. I'll have a key. I'll post this thing. I'll clean it up. I had a typo in there or two, so I'll clean it up and post it in Moodle if you want to look it over too. It'll be there. All right. So any questions on that? You doing all right? Okay. All right. All right, let's have a look at this thing we got coming up on Friday then. So let's kind of, all right, so you should be able to figure out, know how to handle a couple, all right? A couple is a pure moment with no associated force. I'm on the front page of the preview for the midterm. Okay, so no associated force, just a pure twist, a pure moment. They have the same magnitude anywhere on the object. You also don't need to include a moment arm when you put them in a moment equation. You don't want to include them in the force equation. There's 3 pages. All right, so that's how you handle couples. And look at the units on them. They've already got the meters in. Okay, that's how you handle couples. Distributed loads. You find the area of the loading diagram, which is the total force. Apply the force at the centroid of the loading diagram. Centroid of a rectangle is in the middle. Centroid of a right triangle is a third of the distance over from the right angle. Okay, resultants. What you do, you sum up forces in the x and the y, sum the moments. The resultant force is found by theorem of Pythagoras. The angle is found using an arctan. You can also find an offset distance. The resultant is the action, what you're doing to something. That's what the resultant is. Okay. Okay, then we did free body diagrams. Just know the different connection types and what sort of forces they exert on an object. Okay. 2D equilibrium. Start with a free body diagram. Work out the x and y dimensions from the point about which you'll take moments to the forces and find the moments. The moments are an x force for the y moment arm or a y force for the next moment arm. If your answer looks funny, check your moment arms. I've seen, fairly common error to forget to include moment arms in a moment equation. What that'll do is blow your answers up. They'll start looking way out of proportion to what was given initially, okay? So remember, just check that if your answers look odd, okay? 3D equilibrium, start with a free body diagram. Sum of fx is 0, sum of fy is 0, sum of fz is 0, and you have the 3 moment equations. You can do the 2D approach or a full vector approach on those. Okay. Trusses, we did method of joints. Find the reactions and angles first. Draw up a free body diagram of each joint and work your way through with sum of fx and sum of fy. Set the equations up and work through them. Remember, members are all in tension, meaning they pull on both joints they are attached to, or they're all in compression, meaning they push on both joints they're attached to. They're one or the other. Yeah?
How much time will we get on Friday? Just 50 minutes?
Yeah. So it'll be 50 minutes. Okay, zero force members, look for unloaded corners with 2 members or unloaded T's with 3 members. This last one here is a little bit of a mouthful, but if you think of the load as being like an extra member, that's pretty much like an unloaded T is what it is. Okay? If you can prove it's a 0 at one side, it's 0. You don't need to analyze the other side. If you prove it's 0 at one of the joints, it's 0. Okay. Method of sections we just went through. All right, so if I were studying for this midterm, the first thing I would do would be to go through and I would be sure I knew how to handle couples and distributed loads. I'd know how to do a basic resultant. I'd be able to draw a free body diagram, but that's kind of an intermediate step in solving for forces. I'd be able to do a 2D equilibrium with trig, we spent a fair amount of time on that, right? So you should focus on that and know that. And then I would focus on Trusses' method of joints. We just went through a bunch of fancy section problems, but if you have to decide how to spend your time, be sure you know how to do the joints. That's really the way you solve a truss generally. Sections are just kind of a fancier method. So, I might have sections, but I'm not going to make it 30 points out of 100, okay? but I might make a truss 30 points out of 100 because I want you to know how to do that, okay? Truss method of joints. So you all with me? Sometimes when I see people study, they start going off on tangents. I'm trying to keep you on the main thing to know, okay? The main stuff to know is be able to do a couple and a distributed load, okay? You should know how to do those, how to handle those, how to analyze them. Should be able to find a resultant, which was a little while ago, but go back and have a look at that stuff. We did the resultants, it was a while back, but we did them. And I have an example of one of those in your review. And then you should know how to do a 2D equilibrium problem with some trig in it. And then you should know how to do trusses with method of joints. This was 221, is what that was.
What about 3D equilibrium?
Well, I might put a little something on there, but we had one problem on it, and that's 10 points max, absolute max would be 10 points. It might not even be on there, because we just did one problem. So don't, that's kind of what I'm getting at. I hate to see people spend 4 hours studying that stuff for no good reason, I want to kind of tell you what the important stuff is, okay? All right. Okay, then Freebody diagrams, that's a step to be able to do an equilibrium problem. You should be able to do that. And sometimes on a problem, I'll say, draw the Freebody diagram, and I'll give you some points for that, okay? So be ready to do that. 2D equilibrium with some trig, I'd expect to see something like that. And then truss method of joints, okay? Now I might throw in a 3D equilibrium, but again, it's not going to be a huge amount of points. So I might throw in method of sections and zero force, but I'm not going to make that, a whole lot of points. You know what I'm saying? I'm just trying to, I want everyone to get a B for sure, to be able to do those basic skills. Start with that, build off of that. Don't go anywhere until you know how to do those things, okay? So let me get some problem numbers there. 221 is the couples. The resultants are 231 through 242. So just so we're all clear on what we're talking about here. Resultants are 231 through 242. Distributed loads were actually 241 and 242. Okay. Freebody diagrams, we drew lots of them, so I won't write down well, actually, no, that was 251 through 255, right? I think. There we go. You all keeping up okay? No, okay. I mean, I can write faster than you can. Who would believe that? We doing all right? Got that? We good? Okay. Okay, Freebody diagrams, and then the 2D equilibrium. We spent a lot of time on that, right? So 261 through 276. And also, a bit of trig on that, okay? I'm sure they'll have some sort of equilibrium problem with trig in it, okay? So just drop pictures. I'm sorry, now? It's 251 through 255. It's when I had to pull those 2 pages out and just sketch them up, that stuff. All right, we're good. All right, and then the 3D equilibrium, we only did one of them. I think it was 281, is that right? Something like that. There's only one problem that we did.
Just where you look down and choose which axis to look down.
Yeah, right, that was looking down the axes. You could have done it vector style too. I think I put the 281, is that right?
Yeah.
Okay, 281. And then the trusses, okay? Trusses, and just be darn sure you can do this, okay? 291, 292, 294, okay? Those are the ones I assigned for trusses. I actually didn't even assign 291. We just did it in class to kind of go over it, okay? And, just be sure you can work through a truss method of joints. For sure, I'll have one of those on there. So just be sure you can do it, okay? Okay. Zero force members, that's kind of an advanced skill, but I might sneak a couple of those on a harder truss problem, who knows. I haven't made it up yet, so I don't know. And then sections was 311, 12, 13. Okay. So we all right with that? That's the topics. Yeah, question there?
On distributed loads,
Mhm.
what's an example of a cut-up composite loading diagram? First.
Cutting up a composite loading diagram on a distributed load. Oh, we've had a few of those. Let me think. Is this it? I'll get it there. Let's see. Yeah, it's like a trapezoidal load typically.
So when you take your triangle out of it and then
Yep.
you do your rectangle. Okay.
Yeah, there's been a few of those, but you ask questions. Let me find one so I can show you all. It sounds. It's on a couple of those equilibrium, at least one of those equilibrium problems I remember. If I can just get there. There we go.
Yeah.
That one.
Okay. Thanks.
262. Okay. Other questions? Okay. All right. You want to look at these examples here? Okay. Now, the first one, you want to read these things, okay? The first one, if you read what it says find the resultant about point A. So we did these a while back, and we've been doing an awful lot of equilibrium, but we also did resultants before we did all this. What the resultant is the action in a physics sense. It's what's done to something. So what I'm asking is, if you take these forces, this distributed load and that angled force in the couple, and apply them to that beam, what's A going to feel? Okay. So what I want you to do is just sum up the forces on this one. And the key word on that is find the resultant. Okay. So, and this comes up sometimes, so I'll kind of mention it. Resultant is the action in terms of physics. And then we have the other word, which is reaction, right? They're different. The action is what you're doing to the object. The reaction is what the supports do because of the action you've applied. So if I take this pencil and I put it in my hand and I pull on it, let's look at that 70-pound force. If I pull on it, let's just keep it all horizontal. If I pull on it this way, which way does the resultant go? Which way does the action go? What direction? Right or left? Yeah, to your right, is that correct? What way does the reaction go? To the left, okay? So they're slightly different ideas. They're just different, so keep that in mind, that vocabulary and what that means, okay? So if I'm looking at, if I just had a pencil in my hand here, and I'm pulling on the pencil, this is the resultant. It's going this way. And what my hand is doing, and I could possibly draw a hand, but I don't know. Here we go. That's going, here's a thumb, okay. It's going that way. That's the reaction, okay? And, they're related. They're equal and opposite is what they are, okay? So just keep in mind the vocabulary there, what those things mean. So this first problem here is to find a resultant. What are the forces doing? So to do that, I just break the forces down. I take what I'm going to do, here's an example of one of those composite distributed loads. I'm going to cut that off and make that 20. I'm not going to get in a hurry and say, the height of the triangle is 50. I'm going to take 50 minus 20. I'm going to say the height of the triangle is 30, right? And then if I really want to be a little careful, I might put 6 feet down here for the rectangle. And what's the base of the triangle? 4 feet, right? Then I'm going to find the areas of those things. Okay? So the first thing I do is I find the area of the rectangle. 20 pounds per foot is the height, 6 foot span. It's 120 pounds. and that's located 3 feet from A, which is half of the 6. Okay, the area of the triangle is 1/2 times the 30 times 4, so that's 60 pounds. And that is 2 feet to get to the vertex of the triangle, so that's 2 feet right there. But then I got to go 2/3 of 6, or 2/3 of 4. And what that is 2.67 feet more to get to the centroid of the triangle. Okay. So the total distance from A is 4.67, 2 plus 2/3 of 4. So are we doing all right with that? So we're getting those downward forces, and there's 2 of them, and I'm also finding their location. Okay. So I've got the one at 3 feet, it's right there, and that is 120 pounds, and then I'm finding the one in the triangle up above, which goes through the centroid of the triangle, and that is, whatever that is, 60 pounds, okay? So once I've got that, I'm going to sum the moment about A. The 120 and the 60 are both going clockwise about A. So here I'm not finding reactions. I'm not putting in a reactive moment at A. I'm just finding the forces, so I'm just summing them up. 120 times 3 is negative. 60 times 4.67 is negative. They're both negative because they're both clockwise. I've got a couple on there. Okay, the couple is 40 pound-feet. Notice I don't put a moment arm on that because it's already got the moment arm in it. That's negative because it's clockwise. And then the last one I've got is the force at the end. It's going up that way. So sine of 36 times 70 times 6 foot for the moment arm. So we all right with that?
Is that just like a cable or something?
Yeah, it might be. Yeah.
70 pounds pulling out those.
Right. Yeah. There could be various sources for that. So then it's just a matter of summing the moments and getting negative 433 pound-feet. All right, then sum of fx is cosine 36 times 70. That's positive because it's to the right. Okay. So it's 56.6 to the right. Sum of fy is 120 and 60 down, so they're both negative, plus sine 36 times 70, which is up. The sum is negative 139, so it's down. So sum of fy is negative 139, sum of fx is 56.6. So if I take negative 139 over 56.6 and take an inverse tangent, I get negative 67.8. Yeah, question?
Why do you not do reactions at A? If you do reactions at A, you get the opposite.
Correct. Right. So it's just a matter of what I'm asking for. There are all times when really what you want is a resultant. You want to know what the net force effect is.
So, but I don't get why you still wouldn't do like reactions. So
Okay.
we're just assuming it's like non-equilibrium when we do this.
Right. Well, okay. Yeah. Okay. I see your point.
If you put the reactions in there, the arrows are the opposite way.
Yeah. I mean
That's how I feel it's attached to.
maybe I could have worded that better. Maybe I could have said, find the resultant of the force system shown at A. Okay?
I mean, I just assumed it was like what we've been doing.
Right.
Which is all the like equilibrium stuff.
Yeah, I understand that. And the one reason you assume that is because we've been doing so much equilibrium. But we were doing problems like this at the beginning, right after the first midterm. And I understand why you're saying that, but I guess the literal answer, if I said, what's the resultant about A, if you included the reactions, it would be 0, you know?
Yeah.
That's what the reactions do. So maybe that's, I understand why you're saying that. maybe I could word this better.
Okay.
I might say,
Yeah,
what
I'm
is,
gonna get it,
yeah.
I kind of get it now, so like
Yeah.
a little bit of explaining.
Yeah. No, it's a good point though, because I think I could have worded that more clearly. And then, if I put that on a test, I'll try to do that. I'll say something like, what's the resultant of the force and couple system shown?
Okay.
Something like that. It's good for me. All right. Other questions on that, comments? Okay. But the key word there is resultant. That's different than reaction. They're different things. So just, Okay. All right. All right, the next one, make the drawing into a free body diagram by showing the appropriate forces and dimensions, okay? So there's the free body diagram part. And then find the reactions at A and C. Have you seen a few like this already? Like how many of these have we seen?
I think we saw one just like this.
Yeah, we saw 3 homework problems, easy. Just a couple examples in class. Okay. So there is a method to this. Figure out the method, okay? The method is, you see a pin joint. Take a moment about the pin joint because 2 of the unknowns act there. Do trigonometry and get the X and Y components of those armatures that you see from C to B and B to A. All right, we good with that? Once you do that, and then you've also got a force on a ramp there. The force, a couple of things. You take 90 minus the ramp angle to get the reaction angle. 90 minus the ramp angle, okay? That's what you do there. Okay. So once you break up those armatures into X and Y dimensions, you're pretty well set up to find the what you want out of this, which will be the distances from A to where each of the forces are applied. You want the X and Y distances because that makes it easier to do the moments. We good with that? Okay. So I just get everything trigged out there, what I do. And then I'm set up to go. And notice I've got dimensions now that'll get me from where I'm going to take moments about, which is C, and I've got them up to B where that one force is applied, and I can also get them pretty quickly to A where the other force is applied. So now I can go ahead and do a moment equation. Okay. So what I've got then is I've got the dimensions now from C to B, which are negative 16.04 that's in the X and 8.17 in the Y. And I've got the dimensions from C to A, which are negative 21.9 in the X and 5.64 negative in the Y. So I've got those dimensions over here. And I can apply a moment equation. And again, I want to encourage you to use this approach. Draw a picture with those dimensions right on there because, like I keep telling you, I've been doing this 30 years and I've seen mistakes, common mistakes that are made by a lot of people. And one of them is they start busting things on their moment equation. They mix the wrong moment arm with the wrong force. And very likely it's because they don't have a sketch. If you have a sketch, you've got to check on that. You can just look at the sketch. Yeah, question there?
Does it have to be in meters when you're working through it, or can you work with it through centimeters and
Just-
get the same answer?
You can work through it in centimeters to get the same answer. Just be sure you show that, when you write your answer down. Be fine. There's, typically we stay in what's called standard units. You don't do centimeters, but you don't have to. It's okay. Okay. So when I work through that, I get RA is 1079. Okay. Now, notice the applied force is 900, the reaction is 1079. They're all kind of in the same ballpark. That makes sense. If you get an answer for RA that says 12,962, you might have lost a moment arm in there somewhere. That's commonly when your answers blow up on you, when they don't look right, when they're way out of whack, you might have forgotten to put a moment arm in your moment equation. So just remember that. Okay. Now, once I did the moment equation and I got RA, I go sum of fx and sum of fy and solve out the other two. We okay with that? You might see something like that on the midterm, so just get the method down. Find a place you can take moments about, do the trigonometry on the different armatures to the forces, and then apply the moment arms and the force components together to get moments. X forces with Y moment arms, Y forces with X moment arms. Okay. We good with that? I could post this thing up in Moodle too, I guess. I can copy it.
This is a video anyways, right?
Yeah, it is, yeah. So you can go through it fast and pause it and all that too. Okay. All right with that? Questions? We got that? All right. Okay. Okay, the truss is next. Okay, now, I'll get you an equilibrium problem for sure. I'll get you a truss problem for sure. For sure, that'll be worth a quarter of the test easy or more, okay? So know how to do method of joints. There is a method to that. It's called method of joints, I guess, so there is a method to it. And learn the steps and apply them, okay? And again, before you go off into studying some sort of crazy sections, know how to do the method of joints, okay? Okay. And again, it's this stuff's all about drawing pictures and Freebody diagrams. That's how you set this stuff up properly. Draw the picture, apply the picture. That's the steps. Okay, find the reactions and the angles first. Okay. So sum of MA, you got the 4,000 times 3 feet, clockwise is negative. 6,000 times 6 feet, clockwise is negative. 2RC. So RC is probably going to be pretty big given that short moment arm to it, and sure enough it is, 24,000 up. Then sum of fx and sum of fy to get the reactions at A. 18,000 down at A for RAY, 4,000 left at A for RAX. Then do the tangents, arctans of the ratios of the sides to get the angles. Okay. Now, the other thing I want to encourage you on this test is show your work. Don't burn time too much on it, but leave steps. Because if there's a lot of steps in this stuff. It's easy to drop a negative sign or something. If I can see how that happened, it's not a big deal. But if I can't, it becomes a deal because I don't have any idea how you get your answer, So just show me how you get there. And just don't overdo it, but just show a reasonable person how you got to where you got. Okay? So what I'm doing there, I'm treating the truss as one whole object, and I'm finding the reactions at the supports of the truss. I'm also finding the angles on the different members there. Questions on that? You doing all right? Okay, now what you want to do then is start in on the truss. You have to start on a place that has two criteria. The first criteria is there's forces that applied there, so you have something to work with. The other criteria is you've got only two unknowns. So you got to start someplace where have a known force and only two unknowns. So there's lots of places to start on this. I'm looking at D and A. Those are the places you could start. And there's no right or wrong place to start. Although I will mention, sometimes in the past I've set up a truss where I only had you find with method of joints 2 or 3 members. And if I asked you on this one to find BD and BC and CD, start at joint D, okay? For some reason in the past, I've had a few people, if I ask them to find two members like these two, for some reason they started over there and kind of worked their way over. I'm not quite sure they were doing that, but you know, get to the north direct solution. So on this one, I'm having to find all the members in the truss because it's a very small truss, okay? So we're starting up at joint D. Okay, when I look at joint D, I draw a Freebody diagram. There it is. Then I notice I've got two x unknowns and only one y unknown, so I'll start with sum of fy, set that equal to 0. So I go sum of fy equals 0. I've got 6,000 down with a negative sign, plus sine of the angle times FCD. So I take the time to write up that equation, and then I solve it out. So FCD will be 10,000. I'm assuming it's pushing up and to the right. My answer comes out positive, so that's correct. It is pushing up and to the right. Okay. So that's going down, that's pushing up to counteract it, to hold the joint at equilibrium. So the applied force is down, the force of the member then is up. Now, when CD pushes up, it also pushes to the right because it's angled, okay? So we get FCD as 10,000 compression. So when we go sum of FX, we get cosine 36.87 times 10,000 minus FBD. I can solve for FBD, then it's 8,000. So what I've got is CD is in compression, BD is in tension. Yeah, question?
So when it's traveling to the joint, it's compression, and traveling away, it's tension?
Yes, right.
Okay.
My general rule of thumb is compression pushes on joints, tension pulls on joints. That's how I think, but your way of wording is fine too. And yeah, that's one of those things you can write on top of a test if you need to, when you get it. There's no problem there. I remember learning this stuff. I repeated that to myself about 100 times just to get it, because I knew, funny things happen on a test sometimes. You start thinking too much or whatever. So get it figured out, okay? We good on that? Okay, so now we got those two, so now we can go somewhere else, okay? We can go to joint B, you can also go to joint C, it really doesn't matter now. Okay, I went to joint B. There's my Freebody diagram. Sum of fx is 0, I can get AB that way. I start with sum of fx because I've got only one x unknown. I've got two y unknowns. So I don't want to start with sum of fy, I want to start with sum of fx. Okay. We doing all right with that? Okay. And now there's only one unknown left, and that's AC. So you could go to either joint C or joint A. I don't know, it's up to you. I'd probably go to A because C is a little bit more crowded. It's got more stuff going on, but whatever. Actually, it doesn't make any difference. They're both pretty much of equal difficulty, so you could go to either joint. It doesn't matter. Okay. I went to joint A, 4,000 left, 2166 right, and then FAC left. Sum of FX to solve it out. Then I did sum of FY to check it. Okay. Questions on that? Doing all right? Okay. So that's the basic method of joints there. That's how you solve out a truss. Okay. Now the last one there is a little trickier, obviously. Yeah.
So, as we looked from D, when we first, we saw that BD is a compression force.
Tension.
Tension. BD.
Or sorry, It's okay.
So
So
it's
from
pulling
B,
on
so
both.
from B, it would be compression, right?
Right, yeah.
Okay, so it's traveling the same way you do.
I don't know, there's so many ways to express it. Yeah, if this is in tension, it's all tension, it pulls on both joints. If this is compression, CD is compression, it pushes on both joints. Is that good?
Yeah.
There's so many different ways to word it, you know?
Yeah.
Okay, all right. We're good? Okay. Yeah, the arrows go in opposite directions. The two arrows will always go in opposite directions too. I mean, you know, you'll notice the arrows on BD, one goes to the one on the D goes to the left, the one on D goes to the right. They're both pulling.
Yeah.
Okay. Okay. Last one. Okay, a lot going on there, obviously. Now, what I'm doing there, I'm testing method of sections on this. The way I'm doing that, just so you all know, is when I put these panels in here with X's, you can't get through those with joints. You just can't solve them. There's too many unknowns. So you see something like that, you got to use sections. Okay? Now, what I'm asking you for is to find DF. That's that one. And then I'm also asking you to find PM. That's that one. All right, so I'm going to scan this thing over. I'm going to look for zero force members. Do you see any zero force members on that one? Maybe? What's that? MQ, yeah. Now, do you see that at Q, how that's zero? Because that's an unloaded T at point Q. Do you see that at M? I don't, okay? So that's my point. I can't tell that zero force when I look at M. The only place I can see it is at Q. I can see it pretty readily at Q. It's an unloaded T. So if it's a zero at Q, it's zero. Even though it's quite clustered at M, it doesn't make any difference. So I've proved it at Q, I'm done. I know it's zero. You all with me there? And I kind of want to point that out because, you know, on a zero force, if you look at one side, sometimes you can't see it at all, but you can see it the other side, you can see it zero.
So what about like FG or GF or whatever? Is it supported by those names on it?
F, G, G, F, just too much going on for that one. 5 things at F, 4 things at G, just too much. You can't assume anything there because there's just so many unknowns. And really, I mean, there's 2 parts of zero force members. One is the conceptual part, which is a little difficult, I know, and takes some thinking. But the other part is more just looking at it. It's an unloaded T or it's unloaded corner, and that's it, man. Those are the only 2 places. Unloaded corner with 2 unknowns or an unloaded T with 3, and that's it, you know. And there is this thing in engineering, I finally figured this out a little when I got a little further into school. You don't always have to understand it if you learn how to do it first. Sometimes the understanding lags. And it sounds funny and everyone kind of laughs when I say that, but I'm quite serious about it. If you learn the method and apply it half a dozen times, it'll start to make sense. You'll start to understand it better. So that is a nice thing about our discipline is we focus more on how to do it rather than all the conceptual stuff sometimes. Okay? Okay? All right, so let's look at DF. Let's make a cut through there. And when we do that, what I'm going to notice is I'm going to have this thing over here on the right, on the left, I'm sorry. You could use either side. I'm going to have that, and then I'm going to have these 3 unknowns coming off of there like that. And I got 3 unknowns, so it looks to me like I could take a moment about where those 2 intersect and pick up that top one, DF. I could do that, couldn't I? Or am I doing reactions now? Oops, sorry, I got ahead of myself. Okay, so there we go. There's the arctan of PM there, 33.7 degrees, and then I'm doing some of MA, some of FX, and some of FY to find the reactions. I'm doing reactions there first. I'm sorry, I kind of got ahead of myself. Now, if you were in a hurry, let's say you were taking a test or something, just saying, if you're really in a hurry on this, you could work with the right side and not have to find reactions. If you cut, you can use the right side, you know. I like to find reactions first. It's usually good practice, but it isn't absolutely necessary sometimes. You can use one side or the other. Okay, so I go ahead and find the reactions. Now, once I've got those, then I'll start working on those cuts there. So DF looks to be the simpler of the two, so I'm going to start with that. And I'm just going to make a cut down vertically through that panel, and when I do that, there's my free body diagram right there. And I can see that EF and EG intersect at E. I can take moments about E and solve for DF pretty readily there. Okay, that's how I would do that one. Two of the three, I've got three unknowns when I make that cut. Two of the three act through point E, so I can take moments about E. And what will I get there? I'll get 675 times 4 and 180 times 2. I think I busted something there. I need a negative sign on that right there. And so sum of ME is 0. Hang on there. I've got 675 clockwise and 180. Those are both clockwise, right? Or did I, no, I screwed that up. There we go. The equation's good. Screwed up the diagram. I didn't realize I'd done that. There we go. That's how that ought to look. There we go. That's better now. So I'm sorry, question there? So the 675 goes to the right. That's that wrong.
You scroll so I can see how you solve for the 675.
The reaction there? What I did, I took a moment. I probably started with a moment about A and solved for RB, and then did a sum of FX and got RA, most likely. There we go. Okay, you good? Okay. Okay, so that one's pretty quick. You know, if you can see that the two unknowns intersect at E. Now the other one's a little trickier. This is kind of one of those little harder problems I put in there that are worth, I don't know, 5 or 6 points or something, okay? And that one you got to find that MQ is 0. You got to start with that.
Yeah.
And that's called a K-truss, and those K-trusses can be a little difficult sometimes. And so what I did there, I cut vertically through, and what am I after? I'm after LP, I think. And I'm sorry, oh, is it PM, right? So what I did first was I made cut number 1 like that. I'm making this cut on purpose because I'm cutting through 1, 2, 3 of them that go through N. Okay. So I'm doing that with intent, okay? Because when I made that first vertical cut, what I'm calling cut 2 there, I've got 4 unknowns. So I have to find an independent way to get the other one. This is a little bit like that one I was doing earlier for homework. So I'll make cut number 1 first, and I'm seeing that I've got KN, HN, and MN. They all intersect at N. So when I make that cut number 1, as I'm calling it, I can solve for LP by taking a moment about N. So I got all that stuff coming in at N, and then I can solve for LP by just taking a moment. You see the equation itself is pretty simple. The cut's a little trickier though. So then I get LP is 225. Once I've got that, I can go ahead and take a moment about, do that vertical cut number 2, and then I've got 3 unknowns, 2 of them intersect at R, so I can take a moment about R. And then solve for the one I want, which is PM. Okay. Like that. We doing all right with that? A little trickier, that one. Yeah, question there?
Is that your, okay, I didn't see the Freebody diagram.
Okay, yeah, it's up there.
Okay, so you take the moment about 10, so you can free up the.
Okay. I'm just gonna do this real quick just to pause it. Because we got a long.